the problems mainly. So one or two people have made some mistakes of solving this Ux equal to Cu problems in the last exercise. Okay, so that was they tried to solve it in a different way. That was not correct. So those I have commented already in that exercise. Now let's see the transport equation. So let us begin with some story today. Okay, so how are we going to obtain this transport equation? So basically this equation is of this form: ut plus cux equal to 0. Okay, this is the transport equation. Let us obtain that. How? Let us derive this equation. Okay, using some simple stories. How are we going to do? So let me begin with some story. Some story which you might have studied in your school days or in your childhood. Okay, so a cartoon story. I'll just begin with. So I hope you might have studied this, hear the story. Okay. So this is the story called Ant and Dove story. So what does it doing? Let us see. Okay. Okay. So this is the story of this transport equation also. So what does it, what is the story, what is the mathematical idea which I'm going to explain from this story is as follows. Okay. So you have a ant was there, right? So I say like pollutant is there. Okay. So there is a pollutant. Okay. So you assume that there is an ant. Okay. And there is a river. Okay. There is a river. So there is a pollutant which is flowing. Okay. This river, you can just imagine like even you can just make it like a Delhi air or anything, because this is also kind of fluid, because air is a kind of fluid which we say. So the pollutant, okay, what it is going to do is that it is going to move from one place to another place. Okay, so like you can just imagine there is an ant which is going along the river, wherever the wind was flowing or wherever the stream is going along that side, that pollutant is going to travel along. Okay, so that same thing, like ant is just moving. Okay, the ant is moving in the, suppose the river is going in this direction, it is going to move along that. So this is the idea. So suppose I have a concentration. Okay, the pollutant concentration, I'm going to take it. Some small unit mass, I'm going to take it. Very small unit mass, I'm going to take it. So that we are going to explain it, how it is going to be derived from this one. How are we going to derive this equation ut plus cx? This is the one which you are going to derive. Okay, so this is called the transport equation or advection equation. Let us see that. Okay, so let us assume the following. So let us explain the motions with the constant p. Okay, like the way you have seen, the ant was, once the leaf was kept, okay, the ant was moving in that direction of the river where it is going. Okay, that ant is nothing but the pollutant, we can assume that. So we are going to consider the dynamics of the pollutant. Okay, how the dynamics of the pollutant is going to happen in the stream of water. Okay, like how the ant was flowing in the stream of water, the same way we are going to see it. So let us assume that the pollutant is going along the stream of water at a constant speed. Okay, at a constant speed, let us say c is the constant speed where it is flowing. Okay, now what I'm going to say, I'm going to say u of x comma t. This u of x comma t is going to denote the pollutant concentration of the pollutant, okay, concentration of the pollutant in kilogram per meter. Okay, kilogram per meter, unit mass per unit length. Okay, which I'm going to take at unit time t. At unit time t, I'm going to take. At time t, I'm going to take. So the amount of pollutant in the interval. Okay, what is the amount of the pollutant? So for example, the ant was, I have shown the video, right? The ant was going from here to here. Okay. Now what I'm going to say is that, suppose I'm going to take some interval a comma b, I'm going to take it. In the a comma b interval, what I'm going to check is that, okay, what is where the ant is going from one place to another. The amount of pollutant in the interval a comma b, which I'm going to take it. Okay, how the ant is flowing from that one. So I can see that. So that I'm just going to denote as follows. Okay, so integral a to b, the total amount of the pollutant in that interval, I'm going to take it as integral a to b u of x comma t dt. So this is the interval. Okay, pollutant in the interval a comma b at time t, which I'm going to denote. This is the space variable. Okay, a to b u of x comma t dx. I'm going to take it. So that is the pollutant in the interval a comma b. So this is the amount of pollutant that interval at time t a comma b. So a comma b, which is nothing but, suppose there are some pollutant is going from here to here, and just taking some interval from here to here, how much pollutant is going on. Okay. Now what I'm going to see, due to the conservation of mass, okay, the mass is conserved. For example, the ant is not going to be dispersed or anything. The ant is just going like that. But in the pollutant also, in that interval, it is going to be conserved. Due to the conservation of the mass, what we are going to have is that the amount, this quantity, okay, this is nothing but the, what is this one? This u of integral u of x comma t is nothing but the amount of pollutant in the interval a comma b. Okay, the amount of pollutant. So that is going to be conserved. Means it is not going to change. Okay, after some time delta t. So whatever it is there, so at t it will be here. Okay, at t. So for example, at interval a comma b, I'm going to take. So there will be some pollutant here. Okay, in this interval there will be some pollutant. Now after delta, after some, this is at the time t. Okay, at the time t there is some pollutant is here. Okay, so you can see that I have shown some. Yes.
The interval means, is it the interval of time or interval of area?
Interval of x. Interval of x. A comma b is interval of x only. Okay, because I'm integrating with respect to x only, right? So it is a variable with respect to x only. Okay. Now what we are going to do, the time interval also now it is going to come. This is at time t, we have this one. Okay. Now after time delta t, what I'm going to have at t plus delta t, you have seen that the leaf was moving, right? The leaf was moving in that with carrying that ant, right? So that is going to be in this one. Okay, this is going to be time d plus delta t. So this is also going to be same thing. Okay, the same thing, whatever I'm going to shift, that is going to be reached at this place. Now this ant was moving with a constant speed c. Therefore, this is going to be, the displacement is going to become like, this is going to be, the new interval is going to become like a plus c into delta t, b plus c into delta t. That is going to be your new interval. Okay, this green color is going to be a plus c plus delta t, b plus c plus delta t. That is the new interval for that. So in this one, this is going to be conserved. The conservation I'm going to take, because the delta t is very small, I'm going to take the conservation very, very small. So I'm just making many of the assumptions. So based on that, I'm just going to take it. So that means what it is going to say. So I'm going to have integral a to b u of x comma t dt is equal to integral a plus c delta t, b plus c delta t, u of x comma d plus delta t, because this interval is at the interval t plus delta t, not at t. Okay, into dx in both places. Sorry, dx. Okay, so this is with respect to d plus delta t. Okay, now what I'm going to do, I'm going to differentiate this integral with respect to the variable b. Okay, at the end, I'm just going to differentiate with respect to t, and then I'm just going to make it as arbitrary, and then we'll see that. Okay, so this one you don't need to put even b, you can put some other variable y, and then differentiate with respect to y also. Okay, so I'm just making it as b, so that you will understand what is it going to happen, because this is going to be moved. Okay, it is going to be keep on moving, so you are going to get that. So if you differentiate with respect to b, what you are going to have is that you are going to have u of b comma t, okay, equal to this side, it is going to become like u of b plus c into delta t, comma d plus delta t is going to come. Okay, differentiate with respect to p. So with respect to a, it is not going to be that, because this is going to be vanished. Okay, this is the one we are going to get. So differentiate with respect to b, you are going to get this one. Okay, so that means what it is going to say is that, so suppose I'm keeping a camera here. Okay, I'm just going to keep a camera here. This is a camera I'm just keeping, and then watching it. What is it going to happen? So what this equation is going to say is that, okay, so this equation is saying that the concentration at the point P, okay, I'm going to keep a point camera here. Concentration at the point P at time T is equal to the concentration at the point here. Also, I'm keeping a camera, okay, and checking what is that. So this location, okay. So b plus c plus delta, b plus c into delta t, okay, at t time t plus delta t. Okay, this is at the location b at time t, and here I'm keeping a camera at b plus c delta t at time d plus delta t. Okay, so both are same. That's what it is saying. Okay, the equation is saying that the concentration at the point p comma t and the concentration at b plus c plus delta t at time t plus delta t is same, expected to be same. Okay, so so this is expected because as you have seen in this video, okay, in this video I will just show you again how it is happening. Okay, that ant is flowing. You can see that it is flowing. You consider the pollutant as the ant. Okay, that is going to move in that direction. So that means it is not going to be changed. Okay, so that water containing the pollutant particle flows with the constant speed. You can see that how much the water is flowing, the same velocity, almost the ant is also going to move in. Okay, so there are some assumptions which you are making, and then you are doing. Now this interval I have chosen arbitrarily. Okay, this interval I have chosen arbitrarily. Therefore, A and B are arbitrary. Therefore, B is arbitrary, right? Since B is arbitrary, you can change that B as you wish. So therefore, this one I can just simply write as u of x comma t equal to u of x plus c into delta t comma t plus delta t. I can write it. Okay, since B is arbitrary, it becomes like this. Okay, so therefore, what I am going to have, so I'm just writing this equation as follows: u of x plus c into delta t comma t plus delta t minus u of x comma t, that is going to be 0. Okay, so delta t is a small interval. I'm just dividing. So delta t, that is also 0. Okay, so when delta t tends to 0, suppose delta t tends to 0, then what you are going to have is that you are going to have this equation dv, because here both are changing. Okay, x plus c delta t, t plus delta t is there. So dvu equal to 0 is going to come, where v is nothing but c comma 1. Okay, you can just check that what is it going to come. So when delta t tends to 0 and taking v equal to c comma 1, you are going to get, this is nothing but the directional derivative you are going to get. Okay, that's what you are going to get. So that means what you are going to have c comma 1 into ux ux comma u equal to 0 is going to come. Okay, so that means ut plus cux equal to 0 is going to come. Okay, so that's what we have. That is the transport equation. Okay, that is the transport equation. Okay, we know how to solve this problem. Okay, because we have already seen how to solve this problem. Aux plus buy equal to 0. So we know this problem. Aux plus buy equal to 0. We know how to solve this problem. Okay, so here A is nothing but you can take 1. Sorry, A is nothing but C. Okay, B equal to 1. I'm going to take it. Okay, so what we are going to have is that we are going to have, so the answer for this one we have already seen. So this is going to have u of x comma y equal to f of bx minus a. Okay, so what you are going to have for this problem, then u of x comma t is going to become like f of x minus ct is going to come. Okay, this is going to be the answer for this problem. u of x comma t is equal to f of x minus ct is going to be the answer. Okay, so let us solve some simple problems. Okay, so let us solve some simple problems with the boundary condition. So for this problem, ut plus cx equal to 0 with some Cauchy data or initial condition I'm having. So that is u of x comma 0 equal to x if x belongs to 0 comma 1, 0 if x does not belongs to 0 comma 1. Okay, so this is the initial condition. So we know this is the solution. U of x comma t is equal to f of x minus ct. Okay, therefore u of x comma 0 is going to become, okay, so u of x comma 0 is going to become like, this is going to be f of x. Okay, because here t is 0, this is f of x, but u of x comma 0 is nothing but this one, that is x if x belongs to 0 comma 1 and 0 if x does not belongs to 0 comma 1. Okay, therefore u of x comma t is going to become like f of x minus ct. That means f of x equal to x if x belongs to 0 comma 1. Therefore this is going to become like x minus ct if x minus ct belongs to 0, 1, and 0 if x minus ct does not belongs to 0, 1. Okay, so this one I can rewrite it as, okay, the same thing I can rewrite it as x equal to x minus ct. Same thing I'm just rewriting. Okay, x belongs to ct comma ct plus 1. Okay, 0 if x does not belongs to ct comma ct plus 1. So this is what we can expect that. So you can just imagine that, suppose u of x equal to x comma 0. So what you can expect is that this x above x minus ct means, see, if it is at the initial position, it is x. So what is it going to go? It is going to go along the direction of the river. Therefore, you can expect that this is going to be x minus ct is going to be the pollution is going to be there. Okay, and that direction it is going to be x minus ct. Whence it is going to be ct belongs to ct plus 1. Okay. Any questions on this one? The transport equation derivations or anything? I'll just explain this last graph. Any questions with respect to the pollutant and the transport equation derivation? Any questions? Okay. Yeah.
Sir, this equation is for only the river water or something. I mean, in
You can
any
use it
fluid.
for any field. You can use it. See, for example, if you go to Delhi, okay, you can see that there will be plenty of pollutions will be there where the particles will be moving from one location to another location. So those things also, with many assumptions, you can derive this one. But there is a complicated equation which I have shown you very earlier in the first or second class. I have shown you some of the pollutant equations also. So that is involving some more derivatives also, because here we are solving only first order the transport equation with the assumption that we are just assuming it is only depending on one variable and time. Okay, variable with respect to variable space variable, we are taking x only. With respect to time, we are taking t. So t comma x only we are taking. But once you come to that reality, it is not going to be t comma x only. It is going to be t comma x comma y comma z is also going to be there. Okay, so that means we will be having much more complicated equations once you come to that real cases. T of x comma y comma z will come. In the case of if you want to observe what is the pollutant is going to happen in the city of Delhi or some city in India where the pollution is how that is going to happen. In that case, T of x comma y comma z is going to come. It is not only for that pollutant. You can take any of the transport phenomena where particle is moving from one place to another, or heat is transferred from one place to another place. Like this, many things you can take. Okay. So something which is moving, some transportation which is happening, which you can derive using this one. So let us see in the next one. After this transport equation discussion, we will see next one where traffic flow also can be derived using a similar kind of thing, where some more complications will come. So it will not be no longer a linear PDE. It will become like a quasi-linear PDE. Okay.
Yes, sir.
Is it clear? Okay. Okay.
Yes, sir.
So here, here what we are having is that the what you are expecting is that the initial curve. So the x equal to 0. Okay, this is the initial curve I have. Okay, suppose I have this is the initial curve. X belongs to 0, 1, which I have. Okay, because f of x equal to x, if x belongs to 0, 1, right? So 0, 1, you can expect that this is going to be there. So this is 0 and this is 1. So this is 0 and this is 1. So I can expect that 0, 1, f of x equal to x. So this is going to happen. Now, what that transport equation phenomena is saying, so if you move from time t equal to, so this is a time t 0 I have. Okay, so this will be almost here, of course. Okay, at time t equal to 0 I have. Okay, x belongs to 0, 1. Now, if I move along the next one, okay, so if I just move after certain time, this is going to be like this. Okay, means the same thing. It is going to move. A shift is going to be there. It is going to be shifted. At each time step, it is going to be shifted. Like this, you will be getting at each time step. Okay, at each time, you are going to be shifted. So there will be many such things. So I'm just giving some of the curves. So at every time step, you can just see that how it is going to be that. Means this is the x interval. then after time step, it is going to move from, let us say, like 1 to 2, 2 to 1, 3 to 1, etc. But the graph is going to be almost same. Okay, this is going to be same thing is going to come. Okay, so here all these characteristics, if you take any of this equation, all these characteristics equations are given by, for this equation, you can just see that x minus ct equal to x of 0. Okay, that is going to be the characteristic equation. So means the initial function is moved along, right along the x-axis by ct units. So every time whatever t you are giving, so it is going to be moved. Ct units you are going to move it. Okay, so there will be infinitely many such things you are going to get into, depending on the c and t you are going to get. Okay, so this problem we can generalize actually. Okay, this transport equation we can generalize, as I mentioned. This is a simple some things. So as I mentioned here, I mentioned right t of x comma y comma z. So this is the generalization of that. Not only t of x comma y comma z, you can generalize for n dimensional also. So in that case, it is going to become like ut plus b dot du equal to 0 is going to come. The d is nothing but the directional derivative. Okay, the du. Okay, so this is going to be the general n-dimensional problem where x belongs to r power n and t is greater than 0. One sec. Okay, so here x belongs to r power n and b belongs to r power n. Okay, and u is a function from r cross 0 comma infinity. Okay, to r. Okay, where you use the unknown function. So this is the general n-dimensional problem. Not only for the one-dimensional, you can take it any n-dimensional problem. This is the transport equation in the n-dimensional case. Now what we are going to do, we are going to solve this problem in a similar way. Okay, so we fix any point x comma t. Okay, in r power n comma r power n cross 0 comma infinity. Okay, now we are going to define a curve. Okay, like this, the parametric curve you are going to define z of s equal to u of x plus sb. I'm just doing some trial and thing. Okay, t plus s I'm going to define, and then I'm going to check whether this is going to give me the answer for this one. Okay, I'm just taking some trial and error solution, and I'm going to check it. Now I'm going to check what is dz by ds for this problem. dz by ds is nothing but you have to take the derivative. So d means the total derivative I'm going to take. So du, okay, du of x plus sb comma t plus s dot b. Okay, this is d means this is with respect to space variable. Okay, means x. Okay, x variable, x belongs to r power n, right? So this is d, capital D means with respect to x, the space variable. So du of x plus sb. So I'm just taking the derivative with respect to s. So therefore, this is going to become like du x plus sb is going to come. Okay, into b is going to come. Now plus with respect to t also I got to take because it is a total derivative. So ut into x plus sb in comma t plus s, because here no coefficient, only one is there, so t plus s. Okay, so now what we are going to check whether what is this one. Okay, this is nothing but ut plus b plus delta u, where x belongs to r power n and b belongs to r power n. So therefore x plus sb, this is for arbitrary thing. So x plus sb is also going to be in r power n, and t plus s is also greater than 0 because t is greater than 0 and s is greater than 0. So this is going to be there. So this is true for all x belongs to r power n and t greater than 0. Therefore this is also equal to 0. Okay, so dz by ds equal to 0. That means what is it saying? Z equal to constant function of s. Okay, constant function of s. Okay, and hence what is it going to say? For each point x comma t, this u is constant. Okay, z is constant function of s. Okay, therefore this is constant function of x. Therefore u is a constant. U is a constant on the line x comma t. Okay, with the direction. The direction is nothing but b comma 1. Because here what is the thing? So this if I take it dz by ds equal to 0, dz by dz equal to ds equal to 0. This is nothing but the total derivative. Okay, so if I just rewrite this equation in this format, you are going to have this one. I can write as dvu equal to 0, Okay, the directional derivative you can take. What is v? V is nothing but b comma 1. B comma 1 is the direction. So that means your directional derivative is going to be 0 along the direction b equal to b comma 1. Okay, so that is u is constant on the line x comma on the line through x comma t, this point x comma t, okay, x comma t, with the direction v equal to b comma 1, okay, which is going to belongs to r power n plus 1. Okay, so that is going to be that. So therefore, what you are going to have, okay, what you are going to have, the transport equation, whatever I have, okay, this one we can write it in this way. The together, I'm just going to solve this problem. Ut plus b dot du equal to 0. Okay, and then I have an initial condition u of x comma 0 equal to g of x. I'm just going to generalize whatever we did in the last one. Okay, here x belongs to r power n, t greater than 0. Here x belongs to r power n. Okay. Now what we have, the parametric equation already we have described using this one. Z equal to u of x plus sb comma t plus s. That means the line parametrically it can be represented using this one, x plus sb and t plus s, through the point x comma t with the direction p comma 1. Okay, that's what we have discussed. So now when it hits this plane, when it hits this line, u of x, so the initial condition, okay, when it hits this line, what is it going to have? Okay, when it hits the plane r power n cross 0, when this one hits r comma n cross 0, that means when it is going to obtain, when you put s equal to minus t, this automatically becomes u of x comma 0. Okay, only when s equal to minus t, you are going to get, this is going to become 0. That means you are going to have this condition is going to be, means this is going to be satisfied only when s equal to minus t. When s equal to minus t, it is going to satisfy, it has to satisfy this initial condition. Okay, so that means when s equal to minus t means, what is this one? This is going to become like u of s equal to minus t. So this is going to become like x minus tb comma 0 is going to come. Okay, u of x minus tb, I'm going to find it. What is it going to be there? Since u of x comma 0 equal to g of x for all x belongs to r power n, x minus tb is also a point in r power n. Therefore, this is going to become like g of whatever was here. This has to be replaced with this one. So x minus tb is going to come. U of x minus tb is going to be g of x minus tb. Okay. So therefore, what you are going to have, so you are going to have this u of x comma t is also going to become, okay, this u of x comma t is also going to become like, so this one g of x is x minus tb is nothing but g of x minus tb. Therefore, u of x comma t is also going to become like g of x minus tb. Okay, where x belongs to r power n and t is greater than or equal to 0 is going to come. Okay, so that's what we are going to get it in this problem. That's what we did it in the last one also. Okay, u of x comma t is going to be this one. So almost same thing what we have discussed in the last one. You can see that u of x comma 0 equal to f of x was there. Okay, so same thing, u of x minus tb, it is going to become like g of x minus tb is going to come. So therefore, u of x comma t is going to be g of x minus tb. Same thing what we did it in the last one. Okay, because that is going to be the general solution for this problem. Okay, so if g belongs to C1, okay, if this g belongs to g does not belongs to C1, then there is no C1 solution for this problem. Okay, for this problem there is no C1 solution. So in this case, what you are going to have is that again you will get the same kind of thing. U of x comma t is going to be g of x minus tb, but in this case it is not C1 solution, but we call it as a weak solution. Okay, this is called the weak solution of the one. Okay, this is called weak solution. Okay. Now let us complicate the problem little further. What we are having is that we have some source term is also there. Any doubts on this one? Any doubts? Okay. So next one, I'm just going to make it little complicated. What I'm going to do is that I'm just going to introduce ut plus b dot du equal to f. Some right hand side also I'm going to keep it. Initial condition is as it is, u of x comma 0 equal to g of x. same thing, x belongs to r power n and t greater than 0, x belongs to r power n. So I can use the same, yes, okay. So same problem you can take u of x plus sb comma t plus s, you can take it, okay, z of s equal to, then find what is your dz by ds. So dz by ds is going to become like du x plus sb comma t plus s into b plus ut into x plus sb into t plus s. Okay. Now what is this one? This is going to be in this time. This is not going to be 0. This is going to be f. Therefore, this is going to be f of this one, x plus sb comma t plus s. Because this is ut of, here it is u of x comma t, and this is f of x comma t. Okay. Therefore, wherever this x plus x comma t is there, that you got to replace with x plus sb and t plus s. So therefore, this is going to become like f of x plus b and t plus s is going to come. So therefore, what you are going to have now, what you have is that you have a two thing. Okay. So u of x comma t is going to become like in this problem. So you got to solve the homogeneous part and non-homogeneous part. Okay. So in this case, it is going to become like u of x comma t. Now we'll let us see what is u of x comma t minus g of x minus pt. Okay. So u of x comma t minus g of x, u of x comma t g of x minus bt is going to become like this. I'm going to write as z of 0. Okay. And this is going to be z of minus t. Because z of minus t, so you have u of x plus sb. Okay. So if I put z of 0, this becomes x, this becomes t. Okay. So z of 0, what is z of 0? This is nothing but u of x comma t. We are putting s equal to 0 here. Okay. So therefore, this is going to become u of x comma t. So that's what I have written here. So u of x comma t minus g of x minus pt. What is g of x minus pt? So as per this one, so I can just I got to find what is my u of x comma 0. So u of x comma 0 is nothing but as per this one, I got to write as if I put t equal to minus t, s equal to minus t, this is going to become 0, and this is going to become like my g of x minus pt, because that is going to give me the x minus tb, that is nothing but u of x comma 0. Okay. So this is nothing but g of x minus tb. So that's what, that is nothing but z of minus t. Okay. You can check this one. Okay. Or this is nothing but u of x minus tb comma 0. Okay. Okay. So u of g of x minus bt is nothing but u of x minus tb comma 0. That is nothing but you are going to have this one. Okay. U of x comma 0, and this of minus t is going to come. So therefore, this one z of 0 to z of minus t, I can write it in this way: minus t to 0 dz by ds into ds. You can just take the integral, then you are going to get the same thing, z of 0 minus z of minus t. Okay. So therefore, this is going to become like, what is dz by ds? This is this one. So therefore, it is going to become like minus t to 0 f of x plus sb comma t plus s into ds. So therefore, what is my u of x comma t is going to come? It is going to become like integral minus minus t to 0 f of x plus sb comma t plus s into ds plus g of x minus pt. I'm just pushing it to the other side. Okay. So this one I can write it as integral 0 to t. Okay. I'm just putting the change of variable here. So if you put the change of variable, what it is going to come? This I can write as f of x plus s minus t into b comma s ds plus g of x minus pt. Okay, where x belongs to r power n t. So therefore, in general, if you have a problem ut plus b dot du equal to f, the general solution is that u of x comma t with this condition, u of x comma 0 equal to g of x, and u of x comma 0 equal to g of x. Then the general solution is that g of x minus pt plus integral 0 to t f of x minus s minus t into b comma s ds. This is going to be the general solution for this problem. Okay, it solves the, so this is going to solve the initial value problem. Any questions? Any questions? Okay, again we are going to take some stories. Again, it is similar kind of story only, but little with city traffic, etc. Okay, so that is called Burger's equation. In this one, what we are going to do is that we are going to derive a similar kind of equation. Let us see this one, the Burger's equation. So now what we are going to do is that we are going to derive this quasi-linear equation called ut plus ux equal to 0. So in the transport equation here it was c. In the Burger's equation it is going to be u. Okay, that's what we are going to discuss. Okay, so we are going to derive it using a traffic flow model, okay, which is also known as inviscid Burger's equation. So how are we going to do that? Okay, so let us take a traffic signal somewhere. Okay, so there is a road. Okay, so single lane traffic road is there, where I'm keeping some traffic lights, etc. Okay, so some traffic lights are here. Okay, now what I'm going to do, I'm just going to observe what is the density of the cars. Okay, suppose cars are going in this, some cars are going. Okay, some cars are going here. Okay, so some many cars are going. So I'm just going to observe what is the traffic flow in that route. Okay, so that I'm just going to observe. So what I'm going to denote is that I'm just going to denote rho of x comma t. Okay, rho, which is nothing but the density, is to say rho of x comma t is denoting the density of the cars in x belongs to r. Okay, in x belongs to r, I'm going to take it. Rho of x comma t denotes the density of the cars in vehicles per kilometer in x belongs to r, and t is some time. Okay, time t. So therefore, the number of cars, how many number of cars are going to be there in this interval? So let us take an interval a comma b. In this interval, how many cars are going to be there? That I'm going to take it. Okay, for example, you can say like from one traffic light to another traffic light, you can just take it as some interval and then check it how many cars are between that two traffic lights. Okay, so that means we are going to denote a to b. So a is the interval, a comma b is the interval which I am going to denote it rho of x comma t dx. So the total number of cars, the number of cars which are in the interval a comma b can be written as rho of x comma t, because here it is going to denote the density. So from the density, I'm just calculating this one. Okay, rho of x comma t comma dx. Now v of x comma t. Okay, the cars are going at some speed, right? So v of x comma d is going to denote the velocity. How much fast the car is going, etc. The velocity of the cars in x time t. Okay, that is the v is going to be denoted. So the number of cars. So therefore, the number of cars which pass through at time t. How many cars pass through at time t can be written given as rho of x comma t into v of x comma t. So if I multiply these two, then I can calculate what is the number of cars passed through. So let us fix some camera here. Okay, I'm just going to keep a camera here and then going to observe what is how many. So this is my x. So how many cars are crossing this line? Okay, that I am going to observe that. How many cars are crossing this line at time t, that I am going to observe that. So that is nothing but rho of x comma t into v of x comma t. The number of cars that pass through x at time t is given by this one. Okay. So the number of cars in the interval. So the number of, so this is the assumption I'm going to take. So the number of cars in the interval AB changes as per the number of cars which enters and leaves in the interval. Okay, how many cars are entering and how many cars are leaving. So according to that, it is going to change. So now what I'm going to calculate, I'm just going to calculate what is t by dt of. So how much change the number of cars are going to happen, that I'm going to check it. Rho of x comma t into dt. Sorry, into dx. Okay. So that is nothing but, so this one I can calculate. So this would be same as the number of cars. Number of cars in the interval a comma b changes as per the number of cars which enters A and leaves B. Okay, at time x equal to, at time x, we know that number of cars is passing through that line is nothing but passing through that point x is nothing but rho of x comma t into v of x comma t. Therefore, this is same as the changes between this, how many cars are entering here and how many cars are leaving here. So that is nothing but the difference between these two is going to be there. So that means I got to observe how many cars are entering here, how many cars are leaving here, how many enters, how many leaves. Okay, if I take the difference, that is going to give me the changes in the number of cars in that interval is going to be given. So this will be same as this one. That is nothing but rho of a comma t into v comma t, v of a comma t minus rho of b comma t into v of b comma t. Okay. Now what I'm going to do, I'm just going to integrate this one with respect to time. With respect to time, I'm going to integrate, and again I'm making the necessary assumptions that rho and v, whatever is required for the analysis purposes, that assumption I'm going to make it. Okay, so you need to use the Leibniz rule, etc., because you are going to apply the change of things, etc. So therefore, what I'm going to have, I'm just going to take a in between two interval. I'm just going to observe, for example, between 5 minutes and 10 minutes. I'm just checking what is the things are going to happen. Okay, this integration I'm going to take it. So that is going to become like dou by dou t. Okay, this is going to be using the Leibniz rule. I can just put it over here, x comma t, a comma b, okay, into dx dt. That is going to be, this is going to be t1 to t2, rho of a comma t, v of a comma t minus rho of b comma t into v of b comma t. So this one I can write as integral d1 to t2, okay, integral a to b, dou by dou x of, okay, this is dou by dou x of rho of x comma t into v of x comma t into dx dt. Okay. Now, sorry, there is a minus here because I'm just taking my a comma t. A is front and b is on the last, so therefore I'm taking minus here. Okay, minus is there. So you know from the theory of integral. Okay, from the theory of integral, you know that. So if the integral is 0, then automatically you are going to get f is equal to 0. Of course, if you go for the method theory and all, you will get almost everywhere. But we are sitting in the classical thing, not in the method theoretical one. So what you are going to have is that you are going to have integral t1 to t2. Okay, integral a to b, dou by dou t of rho of x comma t dx dt plus, okay, so I'm just going to put this also here, plus dou by dou x of rho of x comma t into v of x dx dt is going to be there. So I'm just going to put this one as, so this one I can write it as equal to 0. So this one I can write as integral t1 to t2, integral a to b, rho t plus rho v x equal to 0. Okay, so if this is equal to 0, that means what it is going to be true. So this is a t1 t2 are arbitrary and a comma b are arbitrary. Therefore, from this equation, what you are going to get is that you are going to get rho t plus rho v x equal to 0 is going to come. Okay, now what we have is that the v velocity also depend on the density of the car. For example, if there is a traffic jam, okay, the cars will go, the density is very high. Okay, if there is a traffic jam means the density of the car is very high in that lane. Okay, that means many cars will be accumulated. Therefore, your speed will be decreased. Will be just having a neutral, or will be just having just a 1 kilometer speed or 2 kilometer speed, like that you will be moving. Okay, if there is no traffic at all, then your speed will be very high, like you will be going 80 or 90 like that. Okay, more than 60 will be going. So therefore, the velocity also depends on the density of the car. How populated, how much cars are there in that density. Depending on that, it is going to be there. Therefore, what we are going to assume, v is a function of rho. I am going to assume. Okay, so assume that v depends only on rho. There may be other factors, maybe that will lead to little more complicated problem. For this assumption, we are going to assume that v is a function of the density only. Okay, there may be other factors. Maybe the driver may be sick, or the driver may not be concentrating, or there may be some other issues where it may be there. But those things we are not concentrating here. We are just ignoring those factors. We are just assuming that the velocity of the car is depending only on the density of the cars in that traffic lane. Okay, so therefore V is a function of rho only. So if the highway is empty, there is no cars in that car in that one, that means rho is 0, we can assume. Density is 0, means there is no car over there. So in that case, we are going to get V equal to V max. Means what is the maximum speed I can go? I can go at that speed. Okay, V equal to V max. Okay, whatever the maximum speed is allowed in that road, that much speed I can go. V equal to V max I can get. Suppose the traffic is completely heavy. Okay, rho equal to rho max. Okay, rho equal to rho max. In that case, you can't move that car at all because the density is completely high. So that means you can't move the car. You got to stop your car and then you got to stay idle. Okay, so that means V equal to 0. So rho equal to rho max means V equal to 0 is going to be. So therefore, I'm just trying to plot this equation. Okay, I'm just going to write it as a single equation. What I can write is that I can just write a linear equation using these 2 points. I can find a linear equation. So in that case, V of rho is going to become like V max into 1 minus rho by rho max. 2 points are there, so I can find what is the linear equation corresponding to that. So I can see that when rho equal to rho max, this is going to become like 1 minus 1. Okay, so therefore you are going to get 0 here. When rho equal to 0, this is going to become 0, you are going to get V max. So these 2 conditions are satisfied. So this is the linear equation you are going to get. So therefore I can apply this one over in this problem. So therefore this is going to become like rho t plus rho V max. Okay, rho V max into 1 minus rho by rho max into x equal to 0 is going to come. Okay, so if you assume V max equal to 1, okay, whatever it is there, either it is 90 kilometer or whatever kilometer, I'm just going to assume that is 1. Okay, so accordingly I can just scale it down. Okay, whatever is in between, I can scale it down 0.1, 0.2. Okay, if it is 80 kilometer, I can name it as 1. If it is 60 kilometer, then you divide 60 by 80, etc. So this is a normalization I'm going to do. So in this case, what I'm going to take is that I'm going to take V max equal to 1. I'm going to take it. Okay, V max equal to 1. I'm going to take it, and I'm going to take U is equal to 1 minus 2 rho by rho max. I'm going to take it. Okay. So U is equal to 1 minus 2 rho by rho max. I'm going to take it. Now you calculate UT. Okay, you calculate UT and this value rho x 1 minus rho by rho max, etc. Then what you are going to get is that after substituting this one, okay, now calculate what is UT and UX and substitute over here. Then what you will obtain is that you will get this equation UT plus UX equal to 0. This part I'm leaving it as an exercise. So U is given, calculate UT and UX. Okay, then verify that this is going to be the same thing. Okay, these 2 are same. Okay, so just verify that. Okay, verify. I leave it as an exercise. Okay, so you are going to get this equation. So that is called the Burger's equation. This is called Burger's equation. Okay, so it is called implicit Burger's equation with the initial conditions. So I can put some initial conditions also. The initial conditions are as follows. So E of x comma 0 equal to E of x comma 0 equal to 1 minus 2 rho naught by rho max. I'm going to use that. This is the initial condition. I'm going to use it. So if rho naught equal to 0, so in this case, if rho naught equal to 0, you are going to get U naught equal to 1. If rho naught equal to rho max, you are going to get U equal to minus 1. Okay, in the negative side, you are going to get. So this is the one as a basic concept for the traffic flow model. But of course, other parameters you can use it, and then you can make the problems as much more complicated. So here we made some assumptions. So based on that assumptions, we got the results. So this is called implicit Burger's equation. So let us solve this problem. Let us solve this problem for this Burger's equation for some of the initial conditions. Okay, and then we will see some more concepts over here, because this is one of the important problem. It is not only for this traffic flow, it's also an important problem for some of the space shuttles or some of the shock waves, etc. Okay, we'll see that, because it is going to give you some kind of discontinuity, etc. in the later cases. So let us consider this problem: UUX plus UY equal to 1 by 2. Okay, So the initial condition is given as follows. So x equal to x naught of s equal to s, y equal to y naught of s equal to s, u equal to u naught of s equal to s by 4. Okay. So the initial curve, so you got to check the transversality condition. So in that case, you are going to get dx naught by ds into b, dy naught by ds, etc. So you are going to verify that. So in that case, you are going to get 1 minus s by 4, okay, which is not equal to 0 if s is not equal to 4. Okay, if s is not equal to 4, it is going to be. But our s is going to belongs to 0, 1, so no problem over here. Okay, so therefore, you are going to get a unique solution for this problem. Now, what is the characteristic system for this problem? The characteristic system is dx by dt equal to dx by dt equal to u. Okay, dy by dt equal to 1 and du by dt equal to 1 by 2. Okay, so the initial conditions you have x of s comma 0, y of s comma 0 equal to 0, u of s comma 0 equal to s by 4 is that. Okay, so now you can solve this problem. So once you solve this problem, what you are going to get is that again I am giving this an exercise. These are all we have discussed already. So you can verify that x of s comma t equal to st by 4, s plus st by 4 plus t square by 4. Okay, y of s comma t is going to be s plus t is going to be there. So these are all some simple problems. So you can just solve that using ODE. Okay, u of s comma 4 is going, s comma t is going to be this one. Now, what we need to find, we have to write, okay, we have to write s comma, because we have to write in terms of u of x comma y, right? Our problem, we have to write it in terms of u of x comma y. So I have written u of s comma t as s comma t term I have written. Now what you need to write is that you need to find what is your s and t in terms of x comma y. Okay, so for which what you need to do, you solve these two equations. Okay, x comma y is nothing but s, these terms are there. You solve these two equations and then find what is your s and t. So that's what I have found there. Okay, simplify this one. Okay, solve these two equations and then find what is s in terms of x comma y and t in terms of x comma y, and then substitute s and t over here. Then you are going to get the answer. Okay, so this part I am just leaving. You can verify that. Okay, so last 2 minutes. Okay, so now ut plus ux equal to 0 problem. We'll take initial condition at this one. So next class we'll see the shock wave problem. This class will just see the rare factor. I'll just introduce and then I'll leave it. So I'm having a initial condition as a discontinuous thing. Okay, u of x comma 0 equal to 1 if x is less than 0, 2 if x is greater than 0. So this is a discontinuous domain. Okay, u of x comma 0, here it is discontinuous part. I'm not talking about what is x equal to 0, etc. I'm just giving x less than 0 and x greater than 0. So the characteristic system for this problem is as follows. So dx by ds equal to u, or dx by dt. Since t is there, I'm just using s here. Okay, u, and dy by ds, or dt by ds actually, because the variable is here, second variable is t. So dt by ds equal to 1 and du by ds equal to 0. Okay, so du by ds, so from this one, du by dt, you can get it as from this one, du by dt is going to become 1. Okay, sorry, 0. Therefore, u is going to be constant. U of x comma t is going to be constant. Okay, so therefore, what you are going to get, c equal to u of x comma 0 is also going to be there, because x of 0 comma 0 is also going to be some constant. Now dx by dt, what is dx by dt? U by 1, so that is going to be u. Okay, so therefore, what you are going to get, you are going to get dx by dt is also going to be like u of x comma 0 is going to come. Okay, so therefore, what you are going to have, x is going to be u of x of 0 comma 0 plus c is going to come. Some other constant, let me put c1 or some capital C. Okay, so now what I have, x is nothing but, sorry, this is dx, right? Dx by dt. So okay, x is nothing but t into u of x comma 0. Because dx by dt is u, therefore x is going to be ut plus some constant is going to come. So t into u of x comma 0 is going to come, because u is same thing. Okay, u is U is C or U of x. The C is same as this one. C equal to U of x comma 0. Okay. So therefore E equal to C, that that one I'm substituting here. So now obtain the use this in the this formula, use the initial conditions. Okay. So x of t is equal to t into U of x comma 0 plus C1 is going to be there. Therefore, what is x of t is going to be? X of t is going to be t plus, okay, because U of x of 0 comma t into t is going to be there. Therefore, t plus x of 0 is going to come here. Okay. And in this case, it is going to become like 2t plus x of 0 is going to come. So this part I will explain in the next class, okay, because the next one also we got to do. I'll just explain this problem in the next class, okay. So then you got to solve this problem. This part I will explain it in the next class. How do you obtain this one, okay? Then solving for t from this one, what you are going to obtain is that you are going to get t in terms of x and x naught you are going to get it. I will explain this part in the next class once again, because this is same thing for the shock waves also. So in the rarefaction, what you are going to get is that you are going to have two families of characteristic lines which you are going to get it. Okay. So which is going to have like this. Okay. One is going to go in this direction. Another is going to be the daughter lines. What is these links also? I will just tell you, because two families of characteristic lines will be there with the different slopes will be there. Okay. One will be for this one will be for this one. So what is the significance of this one? I will just explain it in the next class. Okay. Because this is very important for the rarefaction and shock waves. So I will explain this in the next class. What is the link between these two? Okay. What is the link between this initial condition and this one? Okay. This is very, very important problem in rocket launching and other things, or even some of the people have died when this problem has become a complicated thing. Okay. So those things we'll explain it in the next class. So rarefaction and shock waves. Any questions? Any questions? Okay. If not, thank you. Let's meet next week, next Monday.